Oh, we just focus now. Enough of
I'm
this.
focusing. You're setting up the iPad.
All right. We left off with fission, correct?
Yeah.
Did we write both reactions down for
Yeah.
fission?
Yeah.
So we should have written U235.
We didn't write down fusion.
I didn't write down the second one.
Wait, I'm confused.
Yeah, I wrote down the first one.
Try English.
Yeah, I wrote down both of them.
What?
Wait, no, that wasn't even
That
part.
was not what you wrote.
You didn't write that down.
You got up to Krypton.
And then you just added some stuff.
I need you to write everything down that I have.
Where is that?
Crap, I didn't leave enough room.
I have a different color
So
pen
we
today.
got 235.92 U plus.
So write that down. Stop talking, please. Write it down. Plutonium is another one we can use. So uranium and plutonium are called fissionable material. That means you can use it for fission. So in nuclear power plants, this is happening. This is what's going on in the reactor core, which produces a lot of heat, which produces the electricity that goes to your house. Some of it, at least. So this top one is, I think, more common. Uranium is natural, plutonium is not. Look over there, Pu is outlined, the bottom 94, that means it's created. It's synthetic. But uranium is natural. So you can actually make plutonium from uranium. But anyways, these are both examples of fission reaction. They both produce barium, but plutonium also produces strontium. This one produces 13 neutrons and a whole lot of energy. So let me just get it all down and explain what's going on here and what we need to know. 139 over 56. Strontium is 88 over 38. And go ahead and make sure you get all that down. So these, again, are examples of artificial transmutation, nuclear fission. And remember, fission is what? Splitting or putting together? Splitting, right. So the neutron here is being slammed, or the word is bombarded. That's what the regents will say. It's bombarded into the nucleus of uranium or plutonium, and it splits into two smaller nuclei, right? Barium and strontium have smaller masses than plutonium and then uranium, right? These are bigger, and they split when they hit them with a neutron. As a result, it gives off more neutrons and lots and lots and lots of energy, lots of heat. So what we need to write down is what we said yesterday. One thing happens and then a lot of things happen. What's that called?
Chain reaction.
Right. This is called a nuclear chain reaction. Nuclear chain reaction. And the thing about nuclear chain reactions, especially fission, humans cannot stop it. We started on purpose to create energy, but we can't stop it. So it is kind of scary. So we cannot stop this reaction. So what do we try and do? Control it. Right, we try and slow it down. We try and control it. Cannot stop this reaction, only try to slow it down. So in a nuclear power plant, you have these things called fuel rods. Fuel rod, I believe, is 3 meters long. Don't quote me on that, but I think that's how long it is. And maybe like that, about that. I don't know what that would be, but so it's pretty, bigger than a quarter as far as around. But anyways, there's these thin rods, and the rods are filled with plutonium or uranium. So these rods are put down into a reactor core, which is underwater, because it gets super, 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 super hot. And if nuclear power plants melt down, what happens?
They explode.
No, they don't explode, but they release this to the environment.
Yeah.
Radiation, right. So, you guys heard of Chernobyl, right?
No.
Yeah.
Really?
I've heard it.
Yeah. In Russia, Chernobyl, the power plant melted down like 40 years ago, 60 years ago. I don't know what it is at this point.
I live in radiation.
Yeah, it's still too much radiation for humans to go there. And 3 Mile Island, that happened in our country. You guys remember the tsunami that hit Japan? I don't know how long ago that was now. 5 years ago?
Yeah.
Fukushima? Their power plant started to melt down because of the tsunami, and they had to evacuate. And then did you guys hear about the workers who had to go help clean it up?
They're dead.
Yeah, they basically knew that they were going to die very soon because they were exposed to such high levels of radiation. But somebody had to do it to kind of save the greater good, right? For the greater good, to save more people.
Were they at least paid
Kind of
off?
sad. I'm not trying to bring everybody down. But anyways, the point is that when these fission reactions, so we're sitting in class, we're learning about it, we got to take the regents, and we're kind of disconnected from real life. This happens in a power plant every day that these things operate, and it's very dangerous. So it gives off radiation. It has toxic waste, radioactive waste. These things are radioactive. These things also, the byproducts, stay hot for like thousands of years. So imagine putting something in a microwave, taking it out, and it stays hot for like a month.
That'd be awesome.
I guess. I mean, that'd be weird, right? So the problem is, stay with me, the problem is not only all the radiation, but all the heat generated. So again, we're really just trying to slow this thing down. So with these fuel rods, okay, so let's go back to the whole point here. These fuel rods are filled with the fuel, uranium and plutonium. We can't stop it, but we try and slow it down, so we put these things in between the fuel rods called control rods and moderators. You don't need to know this for a test, okay? But these control rods and moderators absorb some of these neutrons, because what happens here is we hit this with a bunch of neutrons. I don't know how many, a lot of neutrons. Well, more neutrons start coming off the other side, sort of,
They go bang.
and these hit more fuel rods. So imagine like a bundle of sticks kind of tied up with a string. Okay, you can kind of imagine what that looks like. That's what the fuel rods, so if I had like 100 of these all kind of bundled up, so that's what the fuel rods look like. So when they start ejecting neutrons, they start hitting the other fuel rods. That's called the chain reaction. So if we don't slow down all the neutrons that hit the uranium and plutonium, it'll go too fast. It'll get too hot and melt down, and that's bad. So again, I'm just stressing that's what humans, I say humans, there's probably machines involved too, but that's what they do in the reactors to try and slow it down. Now, the cool thing about this, besides the fact some of this stuff stays hot forever, seems like thousands of years, I think that's cool. Dangerous, but cool. The energy that it generates, what do these power plants use it for?
Put it into the grid so you can.
Right, they give the electricity, but there's no electricity in this equation. So where's the electricity come from? I think I said this yesterday.
No.
It's very simple.
What's the reaction?
Very good. Did I say that yesterday? You just know what you're talking about. You just know. All right. So the energy here is used to boil water. Sounds silly. The power plants just boil water. Nuclear power plants. They use this nuclear reaction to boil water. Water produces steam, Andrew. Good job. And what does the steam do?
Well, you can do many things with steam.
It spins
A
a turbine, or turbine as he says. So actually GE in Schenectady, General Electric, GE, you know the company?
Yeah.
Yeah, they are one of the, I think, if not the most, but one of the best companies in the world for making turbines. And at the end of this reaction, you boil the water, that steam spins turbines. Turbines spin, creating charge. That creates electricity. So, it is kind of cool, I think it's cool, that you start with some uranium, hit it with a neutron, you can get electricity to Kieran's house so you can play video games. Kind of cool.
Pretty much.
Now,
That's so true.
now,
Well,
here's
I
the
play
thing.
Sports, you know.
Yes.
Here's the
Video
thing.
games.
Where is it?
Yeah.
40 million, so I'm trying to put this energy in perspective. 40 million pounds of dynamite. Think about that.
Jesus.
40 million pounds of dynamite. Stay with me. Okay, 40 million pounds of dynamite creates the same amount of energy as 2 pounds of uranium.
No, thank you.
So 40 million pounds of dynamite, you probably fill up the school. Fill up the school, light it up, that would be a humongous explosion. Okay, 40 million pounds. Or you could hold 2 pounds of uranium. So I'm trying to give you some perspective of how powerful this is. And why is it so powerful? Mass converted to energy, we talked about that. So what do you need to know for the regions? Now, in case some of you only care about that, you have to recognize this and say, okay, here's fission, here's fission. So on the regions, which of the following is a nuclear fission reaction? Can you pick it out? Okay, so that's what you need to know for the test. And this, okay, nuclear chain reaction, we're trying to slow it down, all right? So I kind of go on and on and on because it is relevant. There are nuclear power plants in New York State that create energy, and that electricity is probably going to your house. Because I don't know if you know how it works, but we don't get all our energy or electricity from one source. You can do that, but you have to sign up, pay more. Like I know I get some of my electricity from a wind farm, but I have to pay more for my electricity for that. But if you just get it from the normal grid, you're probably getting some from nuclear. So anyways, I spent a little time on it. I think it's important that you understand a little bit about it, besides just what's on the test. All right, so that's fission. We're done with that. What's next?
Fusion.
Fusion, right. Okay, let's write that down. Nuclear fusion.
notes?
I don't know.
I have to say it every day.
I give up. I don't know what to say anymore. All right, nuclear fusion. All right. So, Trevor. Now I talked to you too much.
No, Trevor's a prime example.
We never
Alexis.
talk.
Where in nature, nature's the, put it in quotes, does fusion occur? I'll give you a hint. It doesn't happen on Earth.
I know the answer.
Shh.
Did he say it?
The sun, yes.
Yeah.
So nuclear fusion occurs on the sun. However, look at me, please. I know you're listening. It is not considered natural. It's considered artificial transmutation. Why?
Because you can call any of them any of the four. And
No.
it would be acceptable.
Yeah, but let me clarify that because that is a misconception. So remember those four things we wrote down the other day? Flip back to your notes. Remember the four things: natural decay, natural transmutation,
Artificial.
Oh, yeah.
spontaneous. No, that was not part of the four.
Oh no, spontaneous.
Let me finish. Let me finish. Listen. Natural decay, natural transmutation, spontaneous decay, spontaneous transmutation. You remember those?
Yeah.
That's all natural, meaning those elements do it on their own. Humans do not interact or interfere. Now, artificial, fission is artificial, fusion is artificial. What makes fusion artificial? It happens on the sun, but on Earth,
We assist.
we have to do it. Fusion just doesn't happen on Earth. We have to make it happen. So I need you to understand that before I give you notes on it, that fusion is artificial. It happens in labs, okay? And we can't actually do complete fusion. Complete fusion is like the sun. We can't really do it. I'll explain why.
Because it would be very hot.
So first of all, occurs on the sun. You need to know that. That is something, if you take chemistry with me and you get out of here and graduate and you haven't learned that, you don't know that, I feel like I'm doing you a disservice. So you need to know that. That's like a real life thing people should know. How does the sun do what it does? Nuclear fusion. So, occurs on the sun, and what it does, it takes all the hydrogen that it's made of and it combines them to form helium. That's the general, very basic way to write it. The sun does, it's a little more complicated on the sun, but that's the gist of it. Hydrogen is formed into helium. Now, the two equations that you're going to see on the regents are going to be this one. I'm going to give you two. 2 over 1H plus 2 over 1H yields 4 over 2HE. That's one that you'll see on the regents. It's the same principle. Hydrogen atoms coming together, turning into helium. And then the other one would be 3 over 1H plus 2 over 1H yields 4 over 2HE plus 1 over 0N. So that one is actually more realistic. This is called tritium. This is called deuterium. When you take them and combine them, they turn into helium. Remember, this is nuclear, so we're changing the nucleus. It's not a chemical reaction. So a neutron gets kicked out at the end there. So that one is probably more common, but those are the two you'll see on the regents there, that one or that one. All right. So can anyone tell me why, in real life, we basically can't do this very well? Two reasons. Kieran said one of them. Yeah. So the sun, I hope this is right. I looked it up. It was a long time ago. The sun can do this at 72 million degrees Fahrenheit.
Yeah, it's pretty hot.
That's really hot,
That's a good
okay?
temperature.
Now,
Bad.
if we want, yes, sir.
The sun doesn't do it because it's temperature entirely.
Right.
It uses the
Wait,
pressure.
let me.
Oh.
I wasn't done yet.
Yeah,
Well, I'll share that.
No, but Trevor,
Ooh.
I allow you to steal my thunder. So there's two things. Or,
Late now.
well, there's a couple things, but there's two things that create fusion on the sun that we have trouble doing. One, it's extremely hot. And two, the core of the sun is under immense pressure. What's that pressure do? What's a lot of pressure do?
Build up.
Right. Squeeze, right. So think about this. We have a nucleus of hydrogen. Write this. Why do I put a plus sign there?
Because it's a
Positive.
Right.
positive nucleus.
And we take another nucleus of hydrogen, which is positive, and we want them to go together. What's the problem with that?
Well, you see,
Opposites
they're
should attract,
opposites
and they're not
attract.
opposites.
Right. You ever take two magnets with the same pole and try and push them
They
together?
repel.
Right. But have you ever tried?
I
Yeah.
personally
Yeah.
always just tried to push them.
Every day, every morning. Yeah, that's what I do. I wake up, have my coffee, and try and get those magnets to go together. Now,
I can picture it.
so
Yeah, I love
anyways,
them too.
when I was a kid, I remember in 5th grade, I did some project on magnets, and if they're strong enough, you cannot push them to. They do this. You can't get them together. So the concept is, think about it. Think about it. This does happen, but they don't want to. You take two nuclei and you want them to form one big one. That's fusion. They really don't want to, so it has to be ridiculously hot, and like Trevor said, lots of pressure. So on Earth, it's really hard for us to do this, so we have what's called incomplete fusion. We can't get all of the nuclei to do that. Sometimes it's not stable enough, so it just breaks down. It doesn't stay together. And it's also called cold fusion. What does cold mean?
Cold.
Cooler than the sun. Still really, really hot, but I actually did read something last year that, I forget what, it's always in Europe they always come up with this stuff first, but in Europe these scientists came up with a fusion reaction that was actually hotter than the sun. So that's pretty cool. Now there's something else I'd like to share.
Melt anything?
Well, there are scientists and there are experiments where they're using semiconductors, superconductors, where if you use electric fields and magnets, you can get reactions to hover. Yeah. So in other words, if you have a magnetic field or electric field, and you have particles that are charged, and you have that field around it, they won't touch anything, and they can react just hovering in air.
But I'm still confused on how they made something higher than. Wouldn't that just melt?
No, because it's not touching anything. I just explained that. They use those magnetic fields to hover. It's not touching anything except the air around it.
It's still so hot.
And it's probably a vacuum anyway. Right. So they're worried that this place could completely, melt down. Yeah. But they claim they can get it, they can do it, and they can repeat the experiment.
Yeah, I'd rather not.
So, what do you need to know? You need to be able to tell me this is fusion, not fission. It's very different. Now this requires much more and actually puts out a lot more energy than fission. Obviously. How far away is the sun?
Very far.
95 million miles. Okay, 1 astronomical unit. Can you feel it?
Yeah.
Can you get burned from it?
Yeah.
Yeah.
Every day.
So that's amazing. Okay?
I'm so confused.
Stay with me, stay with me. The sun is so far away, but you can still feel it. This produces way more energy than fission. Way more. Okay? So we're going to write that down. Much more powerful than fission. So the sun is proof of that. Okay? So write that down. Produces more energy than fission. And we're also going to write down what we said about the nuclei there. So it produces more energy than fission, a lot more. And it also very difficult to do on Earth, so very difficult to complete due to positive nuclei combining. So I'm kind of paraphrasing there, but trying to put two positive nuclei together is very, very difficult. They don't want to be together. They're positive, both positive. So now, fission produces radioactivity, radioactive waste. What does fusion produce? Look at the reaction.
Energy.
Energy and give me the element it creates. Helium, which is a noble gas, which is inert. No pollution, no radioactivity, no toxic waste. So scientists think if they can perfect fusion, it will take care of all our energy needs forever. So we wouldn't need fossil fuels anymore, we wouldn't need nuclear power plants anymore. Fission would be the answer. I think that's pretty cool, but there's a lot of roadblocks in the way, because even if scientists perfect the fusion and we can get electricity from that somehow, what's going to be the problem? This is more of
It's hotter than the sun.
more of a ethical type thing, or whatever. What's slowing our country down from using renewable energy all the time?
Us.
The running out of renewable energy? Oh, no, that doesn't happen.
I'm glad you came to that conclusion.
I just kind of,
That's okay. I appreciate your effort in the class.
I kind of just.
You didn't think first. That's okay. You're fine.
Hey, I got it
So,
done.
what's the problem with that?
I don't know. I just say us, people.
We're starting to make.
How come we're not using solar, wind, and water and thermal energy to power our houses?
It's less effective.
Because of us.
No one wants to put the money into it.
I say.
Now this might be a little bit related to
Why are you
politics here,
confusing us
but
all? Donald Trump.
no, the oil and gas companies won't allow it. That's why.
I don't care what they want.
That's people.
Yeah.
Because
So
then
we
they,
were wrong.
because then they won't have like.
Well, anyways, so fusion is the answer. That's my opinion, but there's a long way till we
How
get
do you
there.
mean they
So.
won't allow it? They can't control whether
Then they
somebody
won't get their
starts a
money.
different type of